On Britain's windswept Somerset coast, Hinkley Point C is rising as the country's most ambitious and controversial energy project. It's the UK's first new nuclear reactor in over 30 years, the most expensive ever built in Europe, and when complete, it will power 6 million homes with about 7% of the nation's electricity. But despite the steel, concrete, and engineering muscle behind it, the project's biggest threat hasn't been politics or technology. It's been fish. This is the video of how Britain's nuclear revival collided with environmental law, lost industrial skills, and an unexpected ecological bottleneck, revealing just how hard the path to clean energy really is. A grid under pressure. To understand why the UK is willing to endure such eye-watering costs, it helps to look at the alternatives. Britain's electricity system is under increasing strain. Aging nuclear stations that once provided reliable, carbon-free baseload power are being retired. Wind and solar capacity has expanded rapidly, but these sources are inherently intermittent. When the wind drops or the sun sets, the grid still needs a dependable backbone. Hinkley Point C is designed to be exactly that, a 24/7 baseload generator, producing about 3,200 megawatts continuously once both reactors are operational. In a system trying to reach net zero emissions while maintaining reliability, that constant output is invaluable. Without new nuclear capacity, the UK risks deeper dependence on imported gas and exposure to volatile global energy markets. But Hinkley Point C is also something else. A stress test. After a 33-year gap without building new nuclear reactors, Britain had largely forgotten how to do it. Rebuilding an industry from scratch. The decision to build Hinkley Point C revealed just how much industrial muscle the country had lost. Nuclear construction is not just about pouring concrete and assembling steel. It requires specialized welders, inspectors, engineers, regulators, and a supply chain capable of meeting extreme safety standards. After decades of inactivity, much of that ecosystem had disappeared. Factories had closed, skilled workers had retired or moved on, even regulatory familiarity had faded. As a result, the project was forced to recreate an entire nuclear industry almost from zero, importing expertise, retraining thousands of workers, and rebuilding quality systems that had once been taken for granted. The consequences were predictable: delays, redesigns, and soaring costs. Building a fortress on the coast? Physically, the scale of Hinkley Point C is staggering. The site covers roughly 430 acres, making it the largest construction project in Europe. At peak activity, around 14,000 workers have been on site, supported by their own transport system, medical facilities, and security force. At the heart of the plant are 2 European pressurized reactors, among the most complex machines ever designed to boil water safely. Their containment structures feature double-layered concrete walls and multiple redundant safety systems, each backed up several times over. British regulators, known for their conservative approach, demanded thousands of design changes compared to similar reactors built elsewhere. The result was a plant that uses around 25% more concrete and 35% more steel than its French counterparts. The foundations alone set records. The base slab for the first reactor required the largest continuous concrete pour in British history, surpassing even London's tallest skyscrapers. The rise of Big Carl. To assemble structures of this magnitude, conventional cranes were not enough. Engineers commissioned the world's largest land-based crane, nicknamed Big Carl. Towering higher than the pylons of the Golden Gate Bridge, the crane runs on kilometers of rails and can lift up to 5,000 tons in a single operation. This capability transformed construction strategy. Instead of assembling components piece by piece in harsh coastal weather, massive sections were built inside protected facilities and then lifted into place in one move. The approach paid off. Major milestones followed, including the installation of the reactor pressure vessel, the 500-ton steel core of the system, marking the first time a new nuclear reactor had been set in Britain since the early 1990s. By the mid-2020s, lessons learned on the first unit allowed the second reactor to progress 20 to 30% faster. Just as momentum was building, however, a much smaller, but no less complex problem came into focus. the water problem. Like all thermal power stations, nuclear plants need vast amounts of cooling water. Hinkley Point C will draw around 11.6 million cubic meters of seawater every day, enough to fill an Olympic-sized swimming pool every 18 seconds. To achieve this, engineers bored 3 massive tunnels beneath the seabed. 2 extend several kilometers offshore to pull in cold water, while a third discharges warmer water back into the bay. The system works beautifully on paper. The trouble lies at the intake. The surrounding estuary is a protected conservation area, home to species such as Atlantic salmon, shad, and lamprey. Powerful intake currents risk pulling fish into the cooling system, where they can be trapped against screens or carried through the plant, often fatally. This posed a double crisis. Environmentally, it threatened to violate strict habitat protections. Operationally, clogged intakes could restrict water flow, forcing an automatic reactor shutdown. In nuclear engineering, loss of cooling is not an inconvenience, it is an existential risk. When environmental law meets engineering reality, regulations are clear. The plant cannot operate unless it demonstrates that it will not cause unacceptable ecological harm. Solving that problem turned out to be harder than pouring concrete or lifting reactor domes. Early proposals focused on acoustic fish deterrents, hundreds of underwater speakers designed to emit sound pulses that would drive fish away from intake zones. In theory, it was elegant. In practice, the Bristol Channel's extreme tides and poor visibility made maintenance dangerous. Sending divers to service hundreds of devices in such conditions was judged too risky. A second idea involved creating large areas of new salt marsh to offset fish losses. That solution quickly ran into fierce opposition, as it required flooding productive farmland and threatening nearby communities. By the mid-2020s, advances in ceramic transducer technology offered a third path. These newer devices could be installed and maintained from boats, reducing risk to workers. Combined with redesigned low-suction intakes and systems to safely return captured fish to the sea, the approach was more practical, but far from cheap. The billion-dollar fish controversy. A 2024 review ignited public outrage when it suggested that the full mitigation system could cost hundreds of millions of dollars while statistically saving the equivalent of 1 adult salmon every several years. Although the figure was based on abstract conservation metrics and ignored thousands of smaller fish, the headline stuck. To many, it became a symbol of regulatory excess. $1 billion spent on a fish disco. Under mounting political and public pressure, project leaders ultimately committed to the ceramic transducer solution in 2025. Even so, the full environmental protection package is expected to cost close to $900 million, a staggering sum for a system that produces no electricity at all. So, what do you think? Is reliable nuclear power worth the price? Or should those billions have gone somewhere else? Drop your thoughts in the comments. And if you enjoy deep stories about megaprojects, energy, and the systems shaping our world, like and subscribe.